Hello, Aurora lovers. This is Dale Bone from Dale Bone Imaging, and this is Aurora Hunting 101. Welcome to episode 14. What is the Geomagnetic North Pole? Most people are not aware of the geomagnetic poles or how they can affect the aurora. Let's explore a bit. First, I should say this is a bit more of an advanced topic, but explains one of the key oddities that you might have noticed in an earlier episode, especially the one on where in the world can you see the aurora. When most people think of the Earth's poles, most often they think of the North and South Pole, the geographic poles. This is the axis of the Earth's rotation. The North Pole is where Santa Claus lives. The North Pole points at Polaris, the North Star. It's right in the name. It's a shortened version of the Latin phrase for pole star, Polaris pole. You might also think of the magnetic North and South poles, which is different from the geomagnetic poles. The magnetic North and South are where compasses point. And there's lots of interesting things about them. For example, they move around quite a bit. Every once in a while they reverse. And they're not on opposite side of the Earth. Right now the North magnetic pole is fairly close to the North Pole, and the South magnetic pole is quite a ways from the South Pole. So if you use this compass in the Southern Hemisphere, it might not be as accurate. There is a third pair of poles, and that's what I'm going to discuss today, is the geomagnetic poles, which is based on the Earth's overall magnetic field as it extends out into space. These poles affect the aurora, and it's a bit hard to explain what the geomagnetic poles are. But here's an example of a computer model of the Earth's magnetic field with the Earth's magnetosphere expanding away from the Earth. So this is a computer model. I pulled it off of Wikipedia. I'm sure there are other ones. But the big ball of tangled up things in the center is the internal part of the Earth's magnetic field. Looks like a big mess of spaghetti. And then the southern poles along the bottom, the magnetic field expanding out from the southern pole in yellow, and the northern pole in the north. And that extends far out into space, and that's what forms the magnetosphere around the Earth, and that's what interacts with the solar winds. So the geomagnetic poles is basically the mathematical average of all of those poles. So if you're far enough away, you don't see all the individual strands. They just sort of get averaged out together, and that average theoretical axis for the pole is where it crosses the Earth's surface is the geomagnetic North and South Pole. So on the Earth's surface, the geomagnetic poles do not really have much of an effect, but further from the surface, where the aurora form, the poles mark the center of the aurora oval. And that has a pretty significant impact on the visibility of the aurora. So where is the geomagnetic North Pole? It is in far northern Canada on Ellesmere Island, near Greenland. Most importantly, it's about 10 degrees away from the North Pole. And that doesn't sound like very much, but the North Pole is at 90 degrees. So between the equator and the North Pole, it's only 90 degrees. The geomagnetic North Pole is 10 degrees south of that. That shifts the aurora 10 degrees further south. So let's take a look. This makes more sense on a globe rather than a flat map. So I'm going to use Google Earth to discuss this a little bit. So up here we have the physical North Pole, or axis, Earth's axis of rotation, the geological North Pole, and then this is 10 degrees, just about 10 degrees south up in Ellesmere Island is the geomagnetic North Pole. And as I said, that's a pretty significant portion of the distance between the North Pole and the equator down here. It's not crazy, but it's, 10 or slightly more than 10% of the way down. And that is the center of the Aurora oval. The net effect is the Aurora is 10 degrees further south in much of Canada, and then the same thing would apply to the United States. Anything that's low here is going to be 10 degrees lower in the US as well. That makes Canada one of the best places to see the northern lights. In the summer, the sun doesn't really set, especially in the Arctic Circle or the far north. It certainly doesn't get dark enough to see the aurora. In Canada, you can see the aurora further south, which gives you a longer window to see the northern lights. Where I am, you can see the northern lights all year long, even though the sky does not get completely dark. And to help understand the effect of that a little bit more, let's draw a circle on here. We're going to get a circle. No. Where did my dialog box go? Way over on my other screen. Okay, so if we draw a circle and just minor technical difficulties here. The one thing I don't like about Google Earth is it tends to keep rotating the Earth around when you drag it around. I'm sure there's a easier way of doing this. It doesn't matter too much, but I just sort of want to drag this line down. Circle. So if you project that line down, it cuts through Quebec and then some of the eastern New England states. So that would be the area where you can see the aurora the furthest south. Almost clips the end of Ontario there. I want to draw a circle of, in a previous episode I talked about where in the world you can see the northern lights. And for some, it may not be obvious, but some of them are further north than others. And this is the reason why. So if I draw a circle like this and say save, it'll turn it red for us. We can zoom in and see that the places I mentioned were Fairbanks, Alaska, which is here. So these are all places that are in the oval, and then as you cut, where did my red circle go? My red circle, Fairbanks is there. In the Yukon, you're cutting down south quite a bit. Yellowknife is, or Whitehorse is here. Always getting those two backwards. Whitehorse is here. Come here. Come back here, circle. It goes away and then comes back. It's really annoying. Whitehorse is here, and the circle is somewhere over here. As you cut down, over here we have Yellowknife, which is also very close to that line, and then Churchill, Manitoba is right above here. If I remember it, yeah, right here. You can zoom in and see the Churchill's here, the fort is there. You can see the landing strip. So that explains why Fairbanks, Alaska is a great place, but it's way further north than Churchill. It's because Churchill is fairly close to the, much closer straight south of the geomagnetic North Pole. And then you can follow along the tip of Greenland. Iceland is also very good. And then that circle just clips the Scandinavian peninsula, so this is going to be also under their oval, just the top of very northern Russia. And then just for fun, let's add one more. Why? This thing keeps opening things on the other window. So if I do one further down, so that's going to approximately cut through the area where I live. So we can see the Aurora at KP3. It'll be low in the horizon. KP4, it's usually fairly good. KP5, it'll cover usually half the sky. Ignoring the fact that KP isn't a good measure for that, but so if we look at this now, we see those contour lines, and you can see how visibility, so if it's KP34 here in Saskatchewan, it's KP34 all the way along that curve. So I've been up in Anchorage, Alaska, up in here, and it's not significantly better than central Saskatchewan. It's slightly better, but considering how much further north, it's not that much better. And that let me bring up this. So if we look at the NOAA maps, it's not going to let me zoom in on the one that's up. That's why these maps have this curvature. Same reason you draw a circle from the geomagnetic North Pole, and you end up with maps that look like this. So if you go straight south from us, you end up in South America, Argentina, Chile, and they have they're the continent that extends further south, but they don't have any visibility because they're on the opposite side of the south magnetic pole. It's really New Zealand and Australia that gain from their location. And I don't have the map for that, but if we look at this from see the Aurora, they've drawn KP lines, and you can see how it dips. So that you can see the difference, how different it is if it's on a flat map. But you can see this same dip from above Ellesmere Island, and then it dips away from Argentina because the southern geomagnetic pole is on the other side, over by Australia. Now you don't have great visibility for Australia and New Zealand. You're still quite a ways away, but Tasmania, you know, central Canada is in this area. You know, the 2s, 3s, and 4s. But New Zealand and Tasmanian, occasionally southern Australia, you see pictures from there, but you've got to be in the KP5 or higher range, and that KP5, the Aurora is just going to be on the horizon. And then if you This is a NOAA SEC map, similar. You can see the same effect with the dip in that map. Yeah, the only problem with Canada is much of the population lives down in this area. Toronto, Montreal, Ottawa. That's where the big population concentration is. In Canada, much sparser population out through here. Vancouver is also another big city, but it's already far enough from the geomagnetic pole that the visibility lines are curving up quite a bit. In summary, in this episode we learned about the third reverse pole is called the geomagnetic pole, and the Aurora oval is centered over that geomagnetic pole. The geomagnetic pole is located about 10 degrees south of the actual geologic North Pole, and it's located in Ellesmere Island in far northern Canada. That means that the aurora is most visible in Canada and the US because it's 10 degrees further south than anywhere else on the planet. And then Australia and New Zealand have the similar effect on the other side of the world from the southern geomagnetic pole. This explains why the aurora visibility maps are strangely curved rather than just following the latitude lines. So with that, please check out episode 15, What is a Solar Cycle? And I'm wishing you clear skies and happy hunting.